Hi guys, welcome back to my channel. So today we're going to be having a look at some proofs using vectors, and these are going to be geometric proofs. So generally with geometric proofs, what we're actually looking at is we know that certain shapes have certain properties. So for example, a square, we know a square has 4 sides that are equal lengths. We know that a square has 4 right angles. So when we're trying to prove that something is a square, we need to check that the vectors are actually meeting those qualities or those characteristics. So here we have an example, and we're given 3 points. So we have D, E, and F, and we need to prove that the triangle DEF is a right-angled triangle at E. Once we've done that, we can go ahead and calculate the area of the triangle. So I'm just going to show you the tool. So here we can see our right-angled triangle. Now, just because it looks like a right angle, that is not necessarily a statement of proof. So what I'm going to go ahead and do is I'm going to define this vector here. I'm going to define this vector here, and I'm going to see if they are at right angles or not. And that is going to be sufficient proof in this case, because that's all the questions asked us to do, is to show that this right angle exists at this point here, E. Let's jump into the question. So we have our 3 points, and we can rewrite these 3 points. So this would be going from the origin to our point D, and we can write that in vector form as 6i plus 1j minus 3k. So just as a reminder, these I, j, and k, those are our unit vectors for x, y, and z respectively. So same thing I can do with OE, and I can do the same thing with OF. If I have a look at my triangle here, the vector that I'm trying to find is actually a vector DE, and then I'm also trying to find the vector E to F. So we can do that by using our formula. So if we were to try to find our vector DE, that's going to be equal to OE take away OD. So that's going to give us the following vector. So here we've defined our vector for DE, which is going to be negative 4i plus 2j minus k. Next, we're going to go ahead and we're going to find this vector along here, our EF vector, and we're going to use a very similar formula here. So as a reminder, our vector EF is going to be equal to OF minus OE. So let's find that vector now. Now we've defined our vector EF here. Okay, so just as a little reminder, so this was our corner of our triangle here at E. This was our vector going D to E, and this is our vector here going E to F. So we need to prove that this is perpendicular at this point. So to do that, what we're going to do is we're going to take our vector DE, and we are going to find the dot product with our vector EF. And if we can find the dot product between these two vectors and that dot product is equal to 0, then that means it is perpendicular at this point in between our two vectors here. So just as a reminder, when we do our dot product, we're going to multiply the x components, we're going to multiply the y components, and we're going to multiply the z components, and then we're going to add the 3 together to get our value. So starting with our x components, we have negative 4i and 3i. So negative 4 and 3 is going to make negative 12. Then let's find our y components. So 2 times by 4 is going to be 8. And then we're going to find our z components. So negative 1 times negative 4 is going to be positive 4. Alright, so negative 12 plus 8 plus 4 is actually equal to 0. So in this case, our left-hand side is equal to our right-hand side. And therefore, we can make the statement that our vector DE is perpendicular, we're going to use this symbol here, which means perpendicular, to our vector EF. And so therefore, this is going to be a right-angled triangle. So the second part of our question is, now that we know that this is a right-angled triangle, now we need to go ahead and we need to find the area of the triangle. I've just redrawn my triangle here so we can get a bit of a clearer image as to what we need to do. So now that we know that this is a right-angled triangle, if I was to transpose this, I could probably redraw this triangle like this. So this would be my point E here, this would be my point D, and this would be my point F. So to find the area of a triangle, I'm going to use my formula A is equal to half the base times by the height. So in this case, I can use this vector here, my DE vector, as my base, and I'm going to use this EF vector here as my height. So I'm not actually going to use the negative 4i plus 2j minus k. What I'm actually looking for is I'm actually looking for the magnitude or the length of this line along here. So recall from our two-dimensional vectors, whenever we're trying to find the magnitude or the length of a line, so we use these straight brackets. So this is going to be our magnitude of DE, and that's going to be equal to the square root of our x squared coefficient plus y squared plus our z squared. So in this case, that's going to be equal to negative 4 squared plus 2 squared plus negative 1 squared. So in this case, that's going to be equal to the square root of 21. So I'm going to leave it as square root of 21 because I like to use exact values. All right, same thing. So we need to find our height now. So this is going to be our height here. Let's write this in actually. So this is our base, and this vector EF is going to be our height. And again, we need to find the magnitude of that line. So the magnitude of the vector EF is going to be equal to the square root of my x component squared plus my y component squared plus my z component squared. So in this case, that's going to be equal to 3 squared plus 4 squared plus negative 4 squared. So this is going to be equal to the square root of 41. And again, I'm going to leave that as an exact value. Let's go ahead, let's substitute these values now into our formula. So the area is going to be equal to half of the base, which we worked out was the square root of 21, multiplied by the height, which we worked out was the square root of 41. So our area is going to be equal to 1/2 of 861. And I don't know the units, so I'm just going to put units squared because we are dealing with area. Alright guys, so that is a very brief introduction to proof using vectors. So to summarize, when we are doing geometric proofs, we need to determine what the properties of the shape are to begin with. So for example, for a square, that would be that the square has 4 sides and that all the sides' lengths are equal. So in other words, the magnitude of the sides are the same, and that the vectors are perpendicular to each other. If you wanted to have a look into different properties of different shapes, I can jump into another video to do that. But the point of this video was really just to get an idea about how to start using proof to show that vector is creating a particular shape. Alright guys, I'm going to leave it there. I'll see you in the next one.